Section 3. There's a lot going on in Section 3. What we're building to is the idea of a density curve, and normal density curves in particular. However, there's a lot to talk about first. The idea of a density curve is a curve that approximates the shape of a histogram. You know the sort of thing I mean. If you have a curve that's composed of a lot of bars, then theoretically it could have a reasonably smooth shape, not perfect of course. So we want to talk about the kind of curves that approximate these shapes. However, we do have some background information to go over first, and that's what I'll do in this video. So, Section 3, Part A. First off, I want to talk about standardizing data. This is a minor piece of the puzzle that we're embarking upon at the moment, but this is as good a place to talk about it as any. We've talked about in the previous section unit changes, and we've seen how you can measure things in feet or inches or light years or millimeters and so forth. And of course, it changes the size of the numbers. You know, a couple of miles is an awful lot of millimeters and so forth and so on. And of course there's also shifts. You can add the same number to everybody as well. And we've also seen how unit changes don't change the shape of the data. They move it back or forth, they squish it taller and thinner or shorter and fatter, but the basic shape remains the same. For instance, if it's bell-shaped with one peak, then moving it over this way is not going to change that, and squishing it up taller or thinner, well, basically amounts to making the bars shorter or fatter in the first place, and likewise the vertical scale, right? So those kind of things are very cosmetic. Unit changes change the numbers, but they don't really change the underlying data, and the underlying data has the same shape that it always does. With this in mind, we want to talk about standardizing data. You can think of standardizing as the ultimate unit change. It goes like this. First of all, instead of talking about an absolute scale, let's say your body temperature, degrees Fahrenheit, you can talk about how many degrees above average or below, is your body temperature, with the idea being that a positive number would mean you are above average, and a negative number would mean you're below average. In other words, we can shift, we can subtract the mean from everybody, right? So for instance, you could talk about, what was the other example we did? The swimming pool. You could talk about your height in relation to the to the bottom of the pool, or you could talk about your height in relation to the surface of the water. Add 6 feet, 8 feet, whatever to every number, and so forth and so on. So this is the first idea. If you subtract the mean from every number, then that will tell you not the absolute quantity, but how many, whatever's feet, gallon, above average it is. Positive above average, negative below average. Let's say the average SAT score is 100 points. So if you have 105, then you're 5 points above average. We're literally subtracting 100 from your score. But then we have the fact that certain types of data are more spread out than other types of data, right? Heights of buildings don't vary in the same way that heights of people do, or heights of ants, or distances between galaxies. So what we want to do is we want to divide out by the thing that measures the variation in the data, and that's standard deviation. Now again, median and IQR and so forth, 5-number summary, they kind of dead-ended the previous section, but the idea of mean and standard deviation are always with us. So this is the idea of standardizing a piece of data. If the real-world units are called X, gallons, degrees Fahrenheit, whatever, then we'll subtract the mean, X bar, and we'll divide by the standard deviation, S, or S sub X if you like. And that will give us what we call Z, which is the standardized data. It's well, first of all, we're shifting. Take SAT scores. You know, we're subtracting 100 from everybody. And then we'll divide by the variation in SAT scores, say 15, 16 points. And then that will give you the Z, the standardized data. So it's a unit change, but it's more than that. It's the ultimate unit change. It's a way that you can literally compare things that are unlike. I'll show you what I mean by that with an example or two. But numerically, this is what we do. We start with the real-world quantity, call it X. If there's a couple of them, call it Y. Subtract the mean of the data and divide by the standard deviation of the data. And that will give you the standardized Z. Now let's track the units. Remember, if you add or subtract, let's say, gallons, then you're going to get gallons, right? You can think of units as multiplying along. You know, if you've got 5 gallons, then you can think of it as 5 times gallons, and so forth and so on. So gallons minus gallons is still gallons. The gallons factors out, as it were. So many gallons minus so many gallons is still so many gallons. But again, you can think of the units as multiplying along. So if you've got, let's say, 7 gallons over, well, remember, the standard deviation is also in the same units you've got in the first place, right? So if the data is in gallons, then the mean is in gallons, and the standard deviation is in gallons. They're all in whatever units you've got in the first place. So you can, if you've got a number on top, let's say 7 times gallons, and you're dividing by the standard deviation, let's say 2 times gallons, then the gallons cancel. So in other words, subtracting, you're left with the same units you had in the first place, but when you divide, the units are gone. So Z is technically unitless. It has no units. That's one reason we can think of it as the ultimate unit change, because we literally get rid of units. We make what units you started with irrelevant. Let's take an example. Suppose that X is in feet, and hence mean and standard deviation are also in feet, right? Now let's go back and turn them into inches. Well, now, call it Y, whatever your new X, is 12 times bigger than it was, right? And we know from the previous section that the mean is 12 times bigger than it was, and the standard deviation is 12 times bigger than it was. So on the top, we've got a number that's 12 times what it was minus a number that's 12 times what it was. Just factor out the 12. Now the 12 cancels. So you see that in the end, whether you measured in feet or inches or yards or light years or millimeters or whatever, is not going to affect your answer. It literally doesn't matter how you measured things. Feet, inches, yards, millimeters, light years, furlongs. Regardless of how you go back and change that data, remeasure it, you're still going to get the same Z in the end. So that's one reason it's the ultimate unit change. Yes, it's a unit change like any other. We're subtracting to recenter, and we're dividing, which is just a form of multiplication, to change the size of the units. But in the end, we arrive at the same Z regardless of how we measured things in the first place. Example. Suppose a large population of heights, everybody in a country, has mean height 65.2 inches and standard deviation 2.5 inches. So that tells you the center and the spread of the heights of everybody in this country. Now suppose we've got somebody who's 68 inches tall. So we'll subtract the mean and divide by the standard deviation. Let me pop out my calculator. If we subtract 68 minus the mean 65.2, then we'll get 2.8. And if we divide that by 2.5, then we'll get exactly 1.12. So there you go. So the standardized height of this person in this population is 1.12. Now again, it's technically unitless. Inches minus inches is still inches. Inches divided by inches is gone. So it has no units. However, that's a little abstract. If you want to think of it as something, if you want to think of it as something, then track the math backwards. If you want to get back to X, what we'll do is we'll multiply Z by the standard deviation and add the mean. We'll talk about this a little bit later, but X would be Z times the standard deviation plus the mean. So think about that. 1.12 times 2.5, and then add to that 65.2. That'll get you back to the 68. In other words, that's another way of thinking about the 68. The 68 is 1.12 multiples of 2.5 added on to 65.2, with the understanding that if this were negative, it would be subtracted from. I'll say that one more time. The 68 equals 1.12 multiples of 2.5 added on to 65.2. One more time. The 68 is 1.12 standard deviations above the mean, with the understanding that negative above would be below. 68 is 1.12, this number of z's, standard deviations above the mean. So that, although z is technically unitless, that's one way you can think about the standardized quantity, is that it is the number of standard deviations above the mean. Okay? Let's take another example. Now, the idea, of course, is that you can't directly compare people's heights with the how old they are or things of that nature, right? I mean, it's meaningless to ask whether a person is older than they are tall, right? Is the number that gives you somebody's height bigger than the number that tells you how many years old they are, or vice versa? It's meaningless, right? It means absolutely nothing. If you measure their height in light years and their age in years, then yeah, the height is probably going to be a smaller number. But if you measure their height in millimeters and their age in centuries, then the height is probably going to be a bigger number. What does that mean? Absolutely nothing. It's just got to do with how you measure things. It doesn't reflect anything in the real world. In other words, you can't compare things that are not of the same type. If you're going to ask whether something is less than something else or more than something else, then they better both be gallons or degrees Fahrenheit or cubic centimeters or light years or whatever it is you're talking about. They have to be measured in the same units in order to ask whether one thing is less than another. We can't compare apples and oranges. We can't compare things that are fundamentally of different types. However, we can talk about which one is a higher standard deviation above its mean. There's a good example in the homework problems about comparing batting averages from very different decades. It doesn't really make any literal sense. The rules are different, the biology is different, but you can talk about how good the player was compared to other players at the time and whether they were higher above other players at the time. So this is the idea of standardization. This is the idea of comparing things that literally cannot be directly compared. I'll give you an example of how you can compare apples and oranges. So a quick search reveals that apples in general, I mean all apples, all possible apples, have mean weight 200 grams and standard deviation weight 12 grams. It's just the way apples work. Apples on average weigh 200 grams and their standard deviation is 12 grams. What does this mean? This means if you had a whole lot of apples, on average they'd probably weigh about 200 grams. And if you took their standard deviation, it would be 12 grams. Or if you had all the apples that ever were, their average would be 200 grams and their standard deviation would be 12 grams. More on the differences between actual data and things that is too much to be data a bit later, but that's the idea. If you had millions of apples, if you had all the apples that ever were, then on average they would weigh 200 grams. And you took their data average and their data standard deviation from section 2, then you would get 200 and you would get 12. Likewise, oranges, in general, have mean weight 310 grams and standard deviation 15 grams. Let's think about that. On average, oranges weigh more than apples. On the other hand, on average, oranges vary more in weights than apples. So suppose you have an apple that weighs 217 grams and an orange that weighs 330 grams. Which is the better deal? In other words, is that a better example of an apple than that is of an orange, or vice versa? Now, no one is denying that the orange weighs more than the apple. That's not what we're talking about. If you had the world's smallest watermelon and the world's biggest grape, the watermelon would probably weigh more, but it would still be a very bad example of a watermelon, whereas that was a very impressive example of a grape. So that's what we're talking about. Is this a better apple than this is an orange, or vice versa? They're both above average, notice. 217 compared to 200, 330 compared to 310. But which is further above average? You've got to standardize them before you can compare directly. So we'll standardize. For the apple, we'll subtract its mean and divide by its standard deviation. We'll subtract the 200 and we'll divide by the 12. And that'll give me, rounded to two places, for reasons we'll see a bit later, we'll round these to two places. Rounded to two places, it gives me 1.42. So there's my answer. 217 is 1.42 times 12 plus 200 if you track it backward. 217 is, for an apple, is 1.42 standard deviations above average. So this apple is 1.42 standard deviations above average. Now I put it in parentheses because, again, remember, these technically have no units. This particular apple is 1.42 standard deviations above average. The orange, on the other hand, will subtract his mean, 310, and divide by his standard deviation, 15, which is what, 20 over 15, which is 1 1/3. Call it 1.33. So this orange is 1.33 standard deviations above average. So the apple is above average, I mean this is positive, and the orange is above average, I mean this is positive, but this is more positive. So there you go. The apple is a bigger number of standard deviations above average than the orange is. It's all in the name, remember. Standard deviation, a standard for how much things deviate. This takes into account not only the fact that apples weigh less than oranges, but also the fact that apples vary less than oranges. Taking both things into account, we can say that the 1.42 is more than the 1.33. So this is a better example of better in the bigger, in the weighing more sense, heavier. This is a better example of an apple than this is of an orange. So there you go. There's the idea of standardizing data. One more note that I should mention going forward. This is not going to make an awful lot of sense at this point in the course. It may seem like splitting hairs, but when we get to section 7, it's going to be very, very important. And for the middle part of the course, and for the rest of the course, it'll be very, very important. So, going forward, by which I mean I haven't really made this distinction so far in the notes, but going forward, whenever you have actual data and you take the actual mean of the numbers staring at you and the actual section 2 standard deviation of the numbers staring at you, then we call them by our usual Roman letter notations. For instance, if the height is x or y or whatever letter you're using, call it x, then the mean is x bar and the standard deviation is s. Remember, capital for the concept, lower for the particular number. So x bar for the mean, s, or if there's going to be any confusion or duplication on this score, s sub x, if you want to specify that it's this particular s. So when you're talking about explicit data in front of you, then we use the Roman alphabet, the x bar and the s, for the mean and the standard deviation. Any mean or standard deviation that is not explicitly computed from numbers on the page will use the lowercase Greek m, mu, for mean, and lowercase Greek sigma for standard deviation. You may remember capital sigma was Greek s for sum. Lowercase sigma is Greek s for standard deviation. So the mean and standard deviation of the heights of everybody in a room are x bar and s. The mean and standard deviation of the heights of everybody in the world are mu and sigma. There is a very big difference going forward between sets of data where we've actually got the data in front of us and things that are too big to be data. The heights of everybody in the room, 30, 40, 100, 200 people, can be averaged together. Those numbers can be added up and divided by how many there are. But if I tell you that the heights of everybody in the world, or I said United States here, if I tell you that the heights of everybody in the United States, on the average height of everybody in the United States, for the sake of argument, is 65.2 inches. If I tell you that that on average the height of everybody in the United States is 65.2 inches, if I tell you that the average height of everybody in the United States is 65.2 inches, then the one thing you can be sure of is that I have not added up the heights of everybody in the United States and divided by several hundred million. In other words, it has not been computed from data. So any mean or standard deviation that is not explicitly computed from a set of numbers in front of you, we use the Greek alphabet. Mu for mean, sigma for standard deviation. This is a mu, this is a lowercase mu, and this is a lowercase sigma. This is a very big distinction going forward. I think you can see going forward into the rest of the course that there's a very big difference between the average height of everybody that you look at and the average height of everybody you would like to look at. So it's important to have different notations for those. We'll talk more about that in section 7. Just bear in mind that any mean or standard deviation that is at all abstract, unattainable, in any case not explicitly computed from a set of numbers you have in front of you, we use the mu and the sigma. Okay? So really, for the apples example, this is more of a mu and a sigma type of thing, right? If I tell you that on average apples weigh 200 grams, then the one thing you can be sure of is that I have not measured every apple that ever could be or ever would be. You know, you can think of it as an ideal from the genetics of apples, if you like, or if you want to be less grandiose about it, you can think of it as the average of all apples there have ever been. But in any case, it's not explicitly computed from data, right? So these are really more of a mu and sigma kind of thing. Nevertheless, the principles are the same. If could, would. If we could find the mean and standard deviation of all possible apples as data, this is what they would be. So a very important distinction in the middle half of the course, but this is as good a place as any to mention it. Okay? So I think I will leave off this video here because it's our short introduction to some of the ideas that are going on in section 3. And starting in the next part, I will talk about density curves.